Good day, everyone. We're going to begin discussing electrochemistry. So here's a little bit of an overview, just to give you an indication of what we're going to cover today. So first is going to be redox reactions, so it's just going to be a quick review from what you learned from the past semester. Kind of circling back on number 8 with balancing electrochemical equations. This time we're going to look at it through, a pH or acidic or basic lens. The next thing we're going to look at is what standard potential means. Where electrons are supposed to flow, where they're going to gravitate from, etc. Number 3, how standard potential is measured. Okay, so how you would apply a standard hydrogen electrode to a particular type of metal, we'll say for instance, and see what kind of reduction potential that particular element has, or ion has, if you were. Number 4 is electrochemical cells, so as well as cell diagrams. So basically a shorthand way of writing a voltaic cell, or say a cell with a salt bridge, etc. Okay, then ultimately we're going to look to see what kind of electrical work these types of voltaic cells can produce, as well as that delta G relationship or thermodynamic relationship. Number 6 is electrolyte concentrations and their effect on a cell. Okay, so again, not eukaryotic or prokaryotic cell. These are all simply electrochemical cells. Okay, whether they be electrolytic cells or voltaic cells, we'll get into the difference in a little bit. Okay, one of the last things to look at is actually having the relationship between pH or H plus concentration and actual potentiometry or cell potential. Okay, and then last, balancing electrochemical equations, again through either acidic or basic medium. So let's circle back to last semester, what you learned in chapter 8, I believe. So this is the sort of the mnemonic here. Leo the line goes GER. LEO stands for loss of electrons equals oxidation. Of course, of is not going to be part of that acronym. Okay, and then GER means gain of electrons. So that means that translates to reduction. So that's something I kind of keep in mind if you're thinking of what's a oxidation procedure, what's a reduction procedure or step. Okay, now two things to think about are the half reactions. Okay, so in this instance we have nickel in the ground state, which once it loses 2 electrons, that's what's referred to as the oxidation step. So it's losing electrons. Okay, nickel in the solid state, followed by copper 2+, which is an ion, and that's going to pick up 2 electrons to become a ground state element. That is going to be the reduction step. So copper is basically sponging up those 2 electrons that nickel left off. Okay, so okay. Now on to the standard reduction potentials, or E. Now this degree sign means that that's going to be standard. So when I mean standard, that's under standard conditions. So that means 25 degrees C, 1 atmosphere. And all that should be pretty much standardized and put into a table in the back of your text, which you'll see in Appendix 6. Okay, so this is an intrinsic property for each element, even ions as well. So the question is this intrinsic property exclusive to metallic species? No, we'll see that we're going to be balancing equations with nitrogen, with sulfur, other things other than hydrogen and oxygen. Okay. Now, quick sort of two-part conceptual question, if you will. It says when E standard reduction is most blank, that species is most susceptible to gaining electrons. So that means when this is most positive, right, means the higher the voltage, meaning the higher potential that it has to pick up those electrons. Now conversely, when this standard reduction potential is most negative, that species is most susceptible to losing electrons. Okay, and you'll see that pretty much the division between positive and negative is going to be the hydrogen cell. Okay, now, or not cell, but sorry, rather hydrogen electrode. Okay, so there are two different types of electrodes, which we'll get into here right now. For the transmission of electrons, electrons go from anode to cathode. Okay, so anode to cathode. Okay, so you can think of it like a catheter. A catheter is going to draw whatever from, you know, blood or whatever type of fluid out of you, right? Something. I'm not a doctor. Just hear about these things, right? I'm in perfectly good health. I never have to deal with any kind of procedures. So I think of a catheter, and when I think of, you know, where things are to flow out. Okay, or the species with what kind of reduction potential to the species with blank reduction potential. So that means it's going from lower reduction potential or negative. So either lower, so it doesn't necessarily have to be in the negative or negative voltage. So in other words, something that's more propelled to be a reducing, or supposed to be a reducing agent, is going to get oxidized, and then an oxidizing agent is going to pick it up and be reduced. Okay. Now, once again, just check Appendix 6 in the back of your text for standard reduction potentials and values. Okay, so let's look at standard reduction potentials of an actual cell. Okay, so this is simply this is another way of kind of looking at the flow of electrons. So it's going to be the standard reduction potential of the cathode minus the standard reduction potential of the anode. So in other words, this is where the electrons begin. This is going to be quote unquote negatively charged, and then this is going to be positively charged. So it's going to draw those electrons in this direction. So in other words, this should be initial, this should be final. It's a good way of looking at it. Okay, so how about a cell of nickel and copper? How many electrons are moved, and what is the E cell? Okay, so now we already looked at the half reactions at the beginning of the lecture, so why don't you pause and take a couple minutes and look up the data on Appendix 6 and see what you come up with. Okay, so the anode is going to be the cell potential, standard potential, reduction potential that is going to be lowest. So in other words, we're going to look at the nickel as the anode. Okay, so nickel is going to be negative 0.257. Okay, now notice volts. Notice that there is an N value, so that's going to give you the amount of electrons that come through. Now, it's not really essential when you're talking about how many electrons transmit from one species. Okay, it's always going to have the same potential. It's just a matter of balancing the equation. So In other words, that N factor that you'll see later will come up, and that'll just affect the overall cell potential. When we start getting into factors that kind of either diminish or greaten that or the cell potential. Okay, so now we have our other species, which is copper. Okay, so copper. Now look for the correct one. It should be in the middle of the page. That should be 0.342, so plus 0.342 volts. Okay. Now, again, if we're looking at anode, cathode, it should simply be and again, this is all under standard conditions, assuming. So it should be plus 0.342 volts minus, and I put a bracket here, minus 0.257 volts. Okay, so it should give us a positive value, which makes sense because this is going to be a voltaic cell or galvanic cell, whichever you prefer. Okay. Okay, now that that particular difference is going to be plus 0.599 volts as your answer. Okay, so that's going to be for that particular cell. Again, at standard conditions, 25 degrees C, 298 K, whatever, and 1 atmosphere. Now, in establishing these positive and negative standard reduction potentials, you need a 0 point, like I said before. So, a 0 point must be established through a standard comparison. So, it's through a standard hydrogen electrode again. This should be E to the standard SHE. Okay, so that's the shorthand for it. So that's a way of measuring voltage for a particular type of nucleus. So let's say to measure something, or ion, to measure something suspected to have a blank sign of E red or E reduction, ESHE would have to be the cathode. So that means something that would have a negative sign. Negative. Okay. So in other words, it would flow towards the hydrogen electrode. Okay, so conversely, to measure something suspected to have a positive sign of E red, standard ESHE would have to be the anode. So in other words, those electrons would have to come from that hydrogen electrode and go to the one with a higher reduction potential. Okay, so positive. Okay, so here's just general breakdown or generic representation of notation for voltaic cells. So in other words, that RED that you see right here, this was referred to as the reducing agent. So that means it's the species that's going to give electrons off. Notice how it's in the solid state here. Okay, so then you're going to see its oxidized form, right? Giving N electrons off no matter what count that is. Okay, that's going to be in whole integer denominations, and it's going to go into the aqueous phase. So it's basically fighting back and forth between being aqueous and solid. Okay, and then this is the oxidizing agent. So in other words, this is the species that's going to pick some electrons up and then form your solid. So you're going to see some diagrams of voltaic cells that have a salt bridge that attaches to them. That salt bridge is essentially where the electrons are going to traverse, because those two solutions and electrodes are actually separated. There has to be some kind of physical barrier between them. Okay, so that's where this sort of big double line is. It's a wall, if you will, between the two. Okay, so you can think of sort of a salt bridge connecting one to the other. Okay, so this is porous and some kind of insoluble salt mixture that where electrons can basically traverse from one solution to the other. So to be clear, voltaic or galvanic cells produce spontaneous electrical energy, so that means delta G is going to be negative. Okay. Now electrolytic cells, on the other hand, require an external source or input of electrical energy into the system. So, for instance, the other day, I woke up on the wrong side of the bed, I guess, and it felt kind of apocalyptic out there. So I decided to get in my car and go get some groceries and see if my mind would kind of turn around. Well, the car wouldn't turn, and figured out that my battery was dead. So went to auto parts store. Thankfully, it was still open, and got my I tried to get my battery recharged. Okay, so some kind of external charge was going to be put into that battery again, so it could be reused. Unfortunately, no dice. It wouldn't take up the charge, and I was short $140. So there you go. Okay, so in other words, delta G is going to be positive. It needs some kind of oomph to go forward. All right. Now, with voltaic cells, to calculate delta G of the cell or the electrical work, we simply bridge the standard cell potential with electrical work via the Faraday constant. So, just like gas laws, there's just has to be something there to kind of bridge everything together. Okay, so in other words, it's going to tell you what kind of electrical work you can generate. And then also the number of electrons that traverse is going to make a difference too. So that N factor is going to come into place here. So delta G of the cell is going to be equal to negative N times F. Again, the Faraday constant is going to be expressed as 96,500 coulombs per mole. Okay, so coulombs is a unit of charge. All right, and then E cell. Okay, so why don't you guys take a couple of minutes and take a stab at problem 17.38 on page 812. It says, what is the value of delta G cell? So in other words, take a look at this particular problem that you have here. So you have cadmium, which is going to be presumably a reducing agent because it's in the solid state. You also have solid state here. Notice with the two equivalent of this nickel centered species. Okay, now I would take a good look at what you're seeing in the back of in Appendix 6 and see if you have any type of different E standard cells or standard reduction potential values. So be sure to, in other words, what I'm getting at is be sure that you're picking up the correct one. Okay, so breaking things down systematically, how many electrons are going to traverse, what are the standard reduction potentials of the cathodes and the anodes. Again, check Appendix 6. What is the E standards for the cell? And then what is delta G of the cell when the Faraday constant is 9.65 times 10 to the 4 coulombs per mole. So I'm going to give you a couple minutes to work that out, and then we'll go over it. Pause. Okay, so back to the problem. How many electrons traverse, or how many moles of electrons traverse? Count of 2, right? So CD, or cadmium, goes from solid state, the ground state to 2 plus. So it means it relinquishes just 2 electrons. There's only 1 electron per equivalent for this nickel species to pick up an electron. Okay. Also notice, you can check here, notice how there's this OH group here, 2 equivalents, OH minus, so that means 2 minus is going to account for 2 plus, it's going to strike it out and have net neutral. And then you have 2 electrons that have gone over to this nickel to have 2 hydroxide equivalents attached to it. Okay, so this water is still instrumental in the actual balancing of the equation, which we'll see more of later. Okay, the problem actually gave you a cell potential of 1.2 volts positive. Okay. Now, how many electrons traverse? N is going to be equal to 2, so that means 2 equivalents, or 2 moles of electrons. Okay, so what are the cathode and the anode? Again, take a look at Appendix 6 for that. Now, nickel is actually going to be the cathode because it's the one that's going to take up electrons, i.e., positively charged. And then the anode is going to be cadmium. So cadmium is going to lose the electrons. So what is the E cell? Now, we're already given the E cell, but just to do things sort of more experimentally instead of, or I guess more theoretically as opposed to what they give you. I took 0.52 volts minus negative 0.403, so that's going to come from the anode. And that's going to give you plus 0.92 volts. Okay, so a little bit of a difference. Now, I calculated delta G cell for both. So for that, something to pay attention to or take note of here. So this is going to be in joules per mole, essentially. So in other words, if you're going to convert it to kilojoules, you're going to pace it back 3 orders of magnitude. So it's going to be negative sign times 2 for the count of electrons times Faraday's constant times the actual cell potential. So that's going to be 1.8 times 10 to the 2 kilojoules per mole, factoring in significant figures. And then per what the book gives us, okay, so delta G of the cell. And I'll be specific when I ask this question on an exam or quiz or something. Whether or not I give you a cell potential, or if there's going to be something that you will see that you will have to compute like I did here. Okay, so again, 2 times Faraday's constant times 1.20 volts positive is going to give you 232 kilojoules. Sorry, these should both be negative. Sorry about that. So they'll both be negative, and that means these are going to be spontaneous. Release of energy. Okay, so what I just computed is all good and well under standard conditions, but things are a little bit non-ideal in the real world. So let's take examples of both higher temperature, or let's say offset solution concentrations. We're not going to look so much at temperature, but we are going to look at a manipulation or offset solution. Okay, and especially when we take a look at a particular pH of a solution. Okay, now this is where the Nernst equation comes in. This is what my graduate advisor referred to as the nerd equation. Okay, so the E of cell, notice that you don't have that degree sign that's there. Okay, so what is there is a standard That's where the degree sign is above where that E is. And then you have the non-standard term that I've marked over here. So that's going to be the gas constant, the thermodynamic gas constant times the temperature, which is going to be expressed in Kelvin. Natural logarithm of Q, quotient, you know what that is, over N, which is the count of electrons, times Faraday's constant. Okay. Now, the book has a shortcut way of doing everything under standard temperature, so if you want to use that shortcut, be my guest, but I don't really like to work with memory. I like to work with, you know, what has been put in front of me. So, let's go on to the next page. Okay, so let's look at another problem here on page 813, problem 17.48. So calculate the E cell at 298 K of copper, presumably reducing silver, 2 equivalents of silver. So that means 2 electrons are going to be traversed. Okay, so copper 2 plus is going to result. So in other words, copper is getting oxidized and silver is getting reduced. And when silver plus is equal to 2.56 times 10 to the minus 3 molar, so that's going to be the electrolytic solution, and then copper is going to be 2 plus at 8.25 times 10 to the minus 4 molar. Okay, so recall the Nernst equation. So what is Q, first of all, and then calculate what E cell is to be. Okay, so you have your gas constant, you have your temperature. Figure out what Q is, and then the rest should be a go. Okay, it's just plug and chug. So I'll give you 5 minutes to work on that. Alrighty, so a little to unpack here. So what is Q? Q is equal to our product, which is Cu2 plus. Right, so in other words, what's going to remain in solution? Remember that solids don't count in the actual quotient, so that concentration is going to remain on top, and on the bottom you're going to have Ag, but remember it's going to be squared because you have a 2 coefficient in the front. So it's going to be 2.56 times 10 to the minus 3 molar squared at the bottom, okay, on the denominator. So it's going to give you roughly a value of 126 for Q. Okay. Now back to figuring out the standard reduction potential, or the standard cell potential. Copper is going to relinquish 2 electrons, right? So it's going to let go of 2 electrons, go to 2 plus, and then so that particular standard reduction potential is going to be 0.3419 volts. And then conversely for silver to pick up 2 electrons, so silver is being reduced, copper is being oxidized, okay? So even though it's flipped in terms of, you know, whether it's being reduced to being oxidized, that doesn't change the actual potential of the cell itself, okay? Or sorry, not of the cell itself, but the actual anode or cathode or electrode, whatever. Okay, so the standard reduction potential of silver is going to be 0.7996 volts. Okay, so that's going to be the cathode because it's going to be higher in value than the anode. So remember, it's going to go from a lesser reduction potential to a higher reduction potential species. Okay, so E cell is going to be 0.7996 volts minus 0.3419 volts to give you 0.4577 volts under standard conditions. Okay, remember, we also need to factor in now the non-standard terms. So in other words, what's being amended in the Nernst equation, or the NERD equation, as it were. Okay, so now that we have all of that criteria, we have Q, we have R, we have T, we have N, we have F. Okay, so there are going to be 2 electrons as depicted, what's being traversed, or what's being passed on here. So if we plug all these values in, it's simply a plug and chug. 8.31 joules per mole Kelvin. That's again the gas constant for thermodynamic equations. 298 for Kelvin or temperature. So it's going to be standard temperature. Q value is going to be plugged in. Take the natural logarithm of that. Do the product of the three above, and then just the product of 2, which is the count of electrons times the Faraday's constant. And that should leave you with all of this mess here should leave you with plus 0.0620 volts. Okay, so the difference between the standard cell potential and then the difference of the non-standard conditions. So that's actually going to drop it a little bit in terms of voltage. So it's actually going to be 0.3957 volts. So in other words, that offset, if you will, of concentrations is going to factor in. Okay. Now, with that said, let's try to approximate pH from the voltage or the potential of a particular cell. Okay, so in other words, we're going to look at some kind of test solution to figure out what an actual pH is. So we don't know the actual pH. We're looking to figure out what H plus concentration is. Okay, so 2 electrons are going to be picked up by 2 equivalents of H plus to give you hydrogen gas, which is going to be the more elemental form, if you will, even though we all understand it's a molecule. Okay, so recall that pH is equal to the negative log of H plus concentration. Okay, so here's a question. The E cell is 0.48 volts at 298 K. Okay, so for the following cell. So you have zinc, which is going to be used as a cathode or anode. In this case, it's going to be the reducing agent. So in other words, it's going to be the anode. It's going to be passing over electrons to H plus, as it were. Okay. So, and then platinum here is just a means of measuring or detecting. So that doesn't really factor in. All right. Platinum is going to be conserved. Pretty robust, highly sought after element. Okay. So what is the pH of the H plus solution? So if we have that particular voltage, why don't you guys see if you can pull off what H plus concentration is going to be, and then finally pH. So in other words, what you're really going to need to solve for here is Q. So why don't you pause, take about 10 minutes, and see what you come up with. Alright, so taking a look at the equation I have here, effectively what I did was I took the standard cell potential and I took the actual measured cell potential, which is, remember, 0.480 volts. Okay, so in other words, we have the standard, and then we have the actual measured voltage or potential. Okay, so I moved everything onto the other side. This is all the non-standard conditions stuff. Okay, so in other words, that change in concentration should really be what's going to be factored in or analyzed. Okay, so again, we're looking at H plus concentration here. Now, the difference here is something we'll get into down the road, but let's just try to configure some algebra here. So ultimately, we're going to be looking to solve for Q because H plus is going to be what's right here. Okay, so H plus is the variable we're looking to solve for. Now, so in other words, multiply both sides by count of electrons times Faraday's constant, divide both sides by R and T. Okay, so in other words, that's how I got to this algebra here, or to this equation. just by some algebraic manipulation here. So there are two electrons that are being passed over. Again, zinc is going to be the reducing agent, and H plus is going to be the oxidizing agent. Okay, so two electrons are being traversed over. Notice how that 2 is right there for the coefficient where H plus is. So that means that's going to be the exponent. Okay. Now back to Q. Q is going to be equal to the concentration of zinc plus, and then H plus is going to be on the reactant side. So in other words, these are both of the concentrations that are going to be in solution. Okay, so product, reactant. Okay, so product, reactant. Now this is also a product, so that's going to be the partial pressure of H2. Partial pressure you can just assume to be 1. This is already mentioned as 1 if you take a look back at the previous page that I had. Okay, so it's going to be 1 molar. So that means everything's just going to be 1 on the numerator, and then denominator is going to be where your H plus concentration is, squared, again, from the 2 coefficient right there. Okay, so the E standard cell, remember that hydrogen, or standard hydrogen electrode, is going to have 0.000 voltage, okay, minus the standard reduction potential of zinc, which is going to be negative 0.762 volts. So that means zinc is really going to be acting more as a reducing agent, right? Or anode. Okay, so in other words, the E cell is going to be 0.762 volts. Okay, so cathode, anode. All right, R value, we got that already. You guys should be well familiar with that. To solve for Q, we're simply going to plug everything in here to figure out what ln Q is. This is coming back up from this equation here. So in other words, I plugged everything in from what we solved. So 2 times Faraday's constant times, this is going to be what was actually read, which was 0.480 volts, minus the standard cell potential, and that's all divided by 8.314 joules per mole Kelvin times 298 Kelvin. Okay, so everything cancels out except for well, pretty much everything cancels out, period, and that should leave you with roughly lnq should be roughly 22.0. Okay, so next thing you want to do is take e to the log, or e to the x of both sides. So in other words, the anti-log to just give you q, strike out that ln. Okay, so that should give you 3.47 times 10 to the 9, which is a pretty large number. Okay, but remember that you have this H plus concentration on the denominator. So in other words, if you're to solve for H plus, what you're going to do is you're going to have to take the inverse of everything for Q, that is. So inverse of Q, and then take the square root of it to solve for H plus. So that's what I did here. H plus is going to be equal to Q inverse, so Q to the minus 1. So in other words, 1 over 3.47 times 10 to the 9. So it's going to give you a really low number. Okay, and then if you were to take the square root of that, I'm just going to write the 2 right there. That should give you 1.70 times 10 to the minus 5 molar H plus. Okay, so now that we have that H plus concentration, all we have to do is do the negative log base 10, remember not ln, of 1.70 times 10 to the minus 5 molar H plus, and that should give you 4.77 as the pH for that particular solution. Remember that negative sign is going to negate things to make it positive. Okay, so 4.77 is the answer. Okay, so let's wrap things up by balancing equations. This is going to be under either basic or acidic conditions. So I'm going to break things down sort of in a stepwise fashion here. First thing is to assign the appropriate oxidation numbers to each atom. So in other words, the elements that are actually picking up or losing electrons. And I'll kind of review you guys on what negative and positive charges you could predict from that. Second step is to split the equation into two half reactions. So in other words, what's being reduced, what's being oxidized. Number 3, basically it's a 4-part series here. Complete balance each half reaction by balancing all the atoms less hydrogen and oxygen. Balance the O atoms with water equivalents on the opposite side. Okay, so in other words, for each oxygen that you have there that's missing, you're going to balance it with one equivalent of water, for instance. Okay, and then C, balance hydrogen by adding H plus to one side, so that's going to be under acidic conditions. All right, and then finally D, balance charges by adding the electrons. Okay, so you're going to notice that electrons, you'll notice from the first step essentially how many electrons are going to get transferred over. Okay. And then number 4, add 2 half reactions together, being sure to cancel electrons and species that occur on both sides. Okay. Now, I have this one example for you. So just before we get started, remember that for the ionization for H+, since we're clearly going to be under acidic conditions here, any H that you see that's attached to something else has the possibility of being H+ ionized. Conversely, any oxygen that's right here is going to be equal to 2- in charge. So in other words, for this particular example with nitrate, notice how the whole particle, because this is a polyatomic anion, okay, that's going to have a negative charge, so -1 charge. In other words, there are 3 oxygens, so that means there's a total of 3 times 2-, so it's going to give you -6. So that means if this whole particle were net -1, N is going to be equal to N is going to be equal to 5+. Okay. Now, H2S can be predictably S2-. So remember that sulfur is on the same group as oxygen. So in other words, it's going to be isoelectronic, and it has the ability to pick up 2 extra electrons to comprise a full octet. Even though it's not quite as electronegative as oxygen, it still has that possibility. Okay. So in other words, S2- and N5+ on the reactant side. Going over to the product side, NO2 is going to be a neutral molecule. So in other words, well, it's really more of a zwitterion, but neither here nor there. It's net neutral. Okay, so if you have 2 oxygens, that means 2 times -2 is going to give you -4 for the oxygen charges. Okay, so that means nitrogen has to have a net charge of 4+. Its oxidation number is 4+. So notice how nitrogen has gone from 5+ to 4+. So that means there needs to be a transfer of exactly 1 electron. So it means that nitrogen picked up 1 electron to go up slightly lower in oxidation. Okay, and then that electron had to come from somewhere, so presumably S is now going to be S-. Okay, so we have elemental sulfur here, or S8. So that's going to be something to factor in when we start balancing everything. Okay. Now, to do the half reactions here, this is the second step. So notice how I numbered the steps here on the left. So S2- is going to relieve itself of 1 electron. So N+5 or N5+, whatever, is going to pick up that electron and become N = 4 plus, or N4 plus, sorry. Okay, so first thing we want to do, since we have 8 sulfur equivalents on the product side, we need to equate that on the reactant side. So in other words, we're going to put that 8 coefficient right there. Okay, so 8 equivalents of H2S plus NO3 minus is going to give you NO2 and then S8. So in other words, 16 hydrogens or H pluses have been added onto the left. So you have to actually counter that because we don't really have any hydrogen sources on this side, right? So, or on the product side. So in other words, we're going to add 16 equivalents of H2O here. Notice how we need to go 1 to 1 in terms of how many electrons we transfer over. Okay, so notice how if you have 8 equivalents here, we have 8 equivalents of sulfur, 8 equivalents of sulfur. Now the oxygen is going to offset things. So in other words, we have 16 oxygens here. We need to multiply this by, we need to also multiply nitrogen, this nitrate and NO2 species by 16 as well. Okay, so in other words, we need to balance everything in terms of oxygen counts. Okay. Now the next step, in order to balance everything else out where the water is, we need to add 16 hydrogens onto the reactant side. So in other words, this is going to be under acidic conditions, right? So that H plus is there, is free, and electrons are being traversed between here and here. In other words, this is going to be balanced after this. So the equation is officially balanced. Okay. Now, in other words, 1 electron is transferred from sulfur to nitrogen per equivalent. Okay. Now, before you try out these next 2 examples here, so I'll move this page up a little bit. So this is going to be under presumably acidic conditions. This is actually going to be under basic conditions. Notice how there's OH here. So I'll give you several minutes to pause and attempt those problems. Also, if you want to take a look at some examples before you get started, pages 774 to 780 have a few examples for you to peruse. And yeah, why don't you take a few minutes, pause, and we'll come back and we will kind of wrap this up. Okay, so before we begin, just wanted to note with the basic problem on the bottom, I'll mark this in the comments section or in the notes. So this should actually be tin hydroxide with 3 equivalents as opposed to 2, so it should be negatively charged. Okay. Now back to the acidic problem, the first problem. So you have 1 equivalent of NO3 minus, and then copper in the solid state, followed by NO, and then copper 2 plus. So in other words, copper has lost electrons clearly, and nitrogen has gained. Now, again, assuming that oxygen is going to be 2 minus each, you're going to have 6 minus for oxygen, and then X amount of positive charge on nitrogen to give you negative, net negative 1. So in other words, N is going to be 5, just like the last time. Okay. And then going on the right side, so NO, that means that nitrogen is going to be equal to O2 minus, so that means N is going to be equal to 2 plus. So N5 plus to N2 plus, that means it's picked up 3 electrons. Okay. Now, it's a little bit more straightforward in the case of copper. It's just losing 2 electrons. So in other words, copper is acting as the reducing agent, and nitrogen is the oxidizing agent. Okay. Now, since there's 3 electrons getting sponged up by nitrogen 5+, and 2 getting left going away from copper in the solid state, there's an inequality. So in other words, we need to cross multiply to make sure that everything's even. So in other words, now we need to have 2 equivalents of nitrate and then 3 equivalents of copper to make sure everything balances out. Okay, so be sure to put those coefficients there with respect to each one and have everything balanced, because we're balancing. Okay, so the next step here is to introduce oxygens, because clearly there's an inequality about the oxygens here. There's 3 here, just 2 here. Sorry, 6 here. Remember, there's a coefficient now. So 6 to 2. So that means we need a total of 4 waters, right, to have our oxygen quantity here. So in other words, 4 equivalents of H2O now are introduced. We need to balance those. Now 8 H pluses. Remember, O is going to be 2 minus in charge. So that means we need to add a total of 8 amounts of H plus. So that's where what you see right here comes into place. So in other words, notice that if it's going to be H plus and 8 equivalents, that means it's going to be under acidic conditions. Okay, so 8H plus 2 NO3 minus, and then 3 equivalents of copper in the solid state to yield 2 NO, 3 equivalents of copper 2 plus, and then 4 equivalents of water. Okay. Now for the basic conditions problem, again, just to make sure everything is properly balanced. I don't know why I had this wrong, but nonetheless, tin is on the reactant side is going to be bunched up with 3 equivalents of OH minus. So that's going to be net negative charge. Okay, so please make note of that. All right. So bismuth is going to be in 3 plus. So to get to the solid state, or sorry, the ground state, it's going to need to pick up 3 electrons. Okay, so in other words, it's bismuth is the species that is being 3 plus is the one that's being reduced to the ground state. Okay, conversely, tin is going to lose 2 electrons, so tin is going to be 2 plus here on the top. So in other words, if it's going to be a net negative charge, remember that OH is going to be OH minus. So in other words, it's going to be 2 plus here, 3 negative here, to be negative 1 for the particle itself. Okay, so this is a complex ion, if you will. All right, now, so in other words, if look here on the right side, so tin has 6 equivalents of OH minus to give it a net charge of minus 2. So in other words, 4 plus and then 6 plus is going to, or 6 minus is going to give you 2 minus as net charge. Okay, so in other words, going from tin 2 plus to N4 or tin 4 plus, it's lost 2 electrons in that process. Once again, we have an inequality here, so that means we have to cross multiply with our coefficients, and in total there's going to be 6 total electrons that are traversed from one species to the other. So in other words, from tin to bismuth. Okay, so 2 equivalents of bismuth to 3 equivalents of tin. Okay, so 2 equivalents of bismuth hydroxide. Okay, so then 3 equivalents of this tin hydroxide anion. Okay, and then 3 equivalents of tin again on the right with this species, and then 2 equivalents of bismuth in the ground state. Okay, the question is here: is water needed? Not necessarily, because what we're really looking at here to equate is the OH concentration. So if we're taking a look at both sides, there's 15 on this side, so 6 coming from here, 9 coming from here for a total of 15 OH. Okay, and then on the right side we have 3 times 6, which is going to give you 18. So we have an inequality here. We have 15 OH equivalents and 18 on the product side. So in other words, we really need to just add a total of 3 OH minus equivalents, and everything is balanced out. Okay? So that's really all to cover with chapter 17. I have other problems I can work with you during office hours if you care to go over a few other examples. Some people have a little bit of trouble with balancing equations like this, so if you have any questions or if you have other examples you want me to go over, I'll be happy to do so with you. But I've provided some examples here for you to work out and work with some of the homework problems and see what you come up with, and come join me on Microsoft Teams. Thank you. Have a good day.